Okay, so thank you again for inviting me for this Russian-Chinese scientific seminar. Probably this is the second or the third seminar, actually. Well, anyway, so today I'm going to present some results on cooperation in dynamic network games. And well, first of all, I would like to note that a lot of applications of conflicts in social and economic system or telecommunication system or other system, actually, they require take into account the structure of interaction among decision makers. Well, they are the decision makers in game theory actually are called players. And when analyze their behavior, everything this has taken into account. So in game theory, such conflicts can be modeled and studied as well using the theory of network games. So today in this talk, well, we do three things. First, we discuss the theory of network games when cooperation of players is not restricted. Second, we present and discuss the mechanism that stimulates players to adhere to a cooperative agreement and thus making the revision of the agreement unreasonable. So the mechanisms that we will talk about provide the time consistency, or even more stronger property, the strong time consistency of the cooperative solution. And at the end, we examine the two applications of network games well, in public goods provision and the market competition. So I start with a very simple, but at the same time, a quite sufficient model that captures all ideas of network formation, network games, cooperation, and time consistency issues. So it will be the two-stage network games. So we will have just quite standard notation. So we have a finite set of players. We have a network where a set of nodes actually coincides with the set of players. So every node is a single player. And we also have the second component is the set of links. So here we specify that this set of links is the set of undirected links. So communications between I and J is quite the same as between J and I. And Nij stands for the set of neighbors of player I. So this is the set of neighbors whom I is connected with in J. Network G. So we use the model of two-stage problem, which was introduced by Petrosyan et al. In 2013. So at first stage, players form a network. So each player offers connections to some possible subset of players Li, and she has at most Li offers. So mathematically, this proposal can be represented as an action profile, as a binary action profile Gi, and thus we can say that after this, all the proposals have been made, a network G is formed. So a link Ij, so a network J consists of all links Ij that are formed when both players, I mean I and J, wish to have this link. And once the network is formed, we move on to the second stage, and there each player I may revise the network, so she can delete some links, and this action is indicated by a binary action profile Dij. So again, so here we can define the links that are kept and that are deleted. Also at this stage, player I chooses an action. So it can be something else which is not related to the communication or the structure of a network. So thus, after this two-stage procedure, we have a network formation stage, and then we have some revision of a network, and then selection of actions. So here there's just a small example So the network which is formed after the second stage, and then it is revised at the first stage, and then revised at the second stage. So players are rewarded only at the second stage according to payoff functions AHI, and here we use the approach introduced in Lamura 2000 to Kearns et al. 2001. So this is called the class of graphical games. So what it is? So the payoff of a player depends on her actions and on actions of her direct neighbors. So this is our initial assumption. And as in classical definition of a strategy, so strategy UI is a rule that assigns her an action at game stage, given a game stage and a network. So at the first stage, when we have no communication between players, the strategy prescribes so a binary action profile, the profile of proposals. And at the second stage, while the network G is formed, so player I chooses the pair. So the first part reflects the revision of the network. The second part is some action at this stage. So when having a strategy profile, we can define a payoff function. This is a function that depends on the profile of strategies. Assuming the cooperation, assuming that all players can cooperate without any restriction, they try to maximize the total payoff, the sum of the payoffs, and then to allocate it according to some way. So for this reason, we have to introduce an additional transfer utility game and V1, where V1 is a characteristic function. So we have to determine this function. And for the set n, for the set of all players, this function represents the amount to be allocated among players. So the cooperative solution is a rule that assigns a subset from an imputation set to this game. And using the classical von Neumann and Morgenstern approach for determining the characteristic function as a solution, as a max-min optimization problem. So here in this two-stage model, the characteristic function is given by so is determined by this expression. So the important thing here to know that the max-min optimization problem is reduced to just a maximization problem, which is more simple from the perspective of computational perspective. Second, we just when following the cooperative trajectory, when passing from one stage to the second stage, we also have to define the characteristic function in a subgame, and similarly it can be done. So the characteristic function is now represented in proposition 2. So the only difference between function V1 and V2 is that here in V2 the network G is fixed. So this is a G bar. This is the network which has to be realized under the cooperative strategy profile. So when players jointly choose their actions to maximize the total payoff in the game. So having these two functions, we can move on to the selection of cooperative solution and then the allocation. But well, here we have some problem of so it's called time consistency problem, which was introduced in 1977 by Leon Petrosyan and for class of cooperative differential games. And in 2013, it was adapted for cooperative network games. So before the game starts, players have negotiated to some cooperative strategy profile, and then to allocate the maximum sum of the payoff using the solution. And this solution realizes an imputation psi I. So this means that in the two-stage game, player I expects the psi I as her payoff. But what would happen if after the first stage of the game, the players revise the imputation? So for this reason, we use the same cooperative solution, but in a sub-game, and just recalculate the solution and take an imputation psi. So now player I's payoff becomes psi I of V2, which is determined by the characteristic function in a sub-game after the revision of an imputation. So a cooperative solution is said to be time consistent or dynamically stable if for any imputation in the initial game there exists an imputation in a sub-game such that they are coincide. Well, there is a more strong property. A solution is called strong time consistent or strong dynamically stable if a solution in a sub-game is just a subset of a solution of the initial game. Well, time consistency actually means that if we have an allocation, if we have agreed on the allocation, so even at the second stage, the same allocation is feasible. Well, actually, not all of the cooperative solutions satisfy this property. Not all of them are time consistent. So for this reason, Petrosyan and Danilov in 1979 introduced a mechanism which was called the imputation distribution procedure. It was introduced originally for cooperative dynamic games, and in 2013 was adapted for cooperative network games. So here, using the considered set in a profile beta is an imputation distribution procedure for the imputation from the solution M, if it satisfies these properties. So the first one says that the imputation is split into two parts, the two payments at the first and the second stage. The second means that the sum of payments at the first stage equals 0 because players are not rewarded at the first stage. And the last condition says that the sum of all payments at the second stage is exactly the sum of the payoffs that player get under the cooperative solution. And an IDP is time consistent if there exists an imputation in a solution from the subgame such that this equality is satisfied. But when we consider a most strict property like strong time consistency, so we say the imputation distribution procedure for psi is strong time consistent if these conditions are satisfied. So here this sign is just Minkowski sum. So it means that whenever profile we take from MV2, so B1 plus this profile belongs to the set M1. So we have a number of results. So there is expression for the explicit expression for the time consistent imputation distribution procedure in a two-stage game. And we also have result that if the cooperative solution that depends only on values Vn and Vi values of singleton is time consistent. So, and the last one is just the statement that relates to strong time consistency. So we additionally require that the cooperative payoff, the profile of cooperative payoffs belongs to the solution of the original game. And some specific results here for the core. When we take core just as a cooperative solution, so if the core of the special game V1 minus V2 is non-empty and the zero vector belongs to the core, and the profile of payoffs belong to the intersection of these two cores. Then the core of the game is strong time consistent, and the similar result is for the characterize the strong time consistent imputation distribution procedure. So given this condition, we can specify, we can define payments to players at both stages and having time consistency. And I want to demonstrate you two examples. First, in the public goods provision. So this is based on the model of Bramulli and Canton, Galeotti, Goyal for one-stage games. So here an action is an effort. So from 0 to infinity, the payoff is a function of a form like benefit minus cost. And this game has under certain assumption, we notice the positive effect from links. So if players add more links, that it is more beneficial for any of them. So they should be greater or equal, sorry. And we have a number of propositions that characterize the characteristic functions. So I'll just keep them. The result, which gives us the time consistency of the solution. So when the number of proposals is the same for all players and equal to n-1, so then two characteristic functions coincide, and therefore it implies that any cooperative solution in the public good provision game is time consistent. And the second class of games, the market competition. So we have two-stage games. So the strategy now is a quantity of a firm where players output a number of items to be produced, and the payoff is a revenue minus cost function form. So again, here we notice that the links create negative effect. So the addition of new links has a negative effect, and players doesn't want to cooperate, establish link between them under cooperation. So here we have some propositions that characterize the characteristic functions V1 and V2. And we notice that these functions coincide, and therefore any cooperative solution in this two-stage market competition game is time consistent. And to conclude, I just want to summarize. So for two-stage network games, we demonstrated that classical max-min characteristic function is determined by the associated maximization problems. So we demonstrated that the cooperative solution to a two-stage network game may not be time consistent. We introduced imputation distribution procedure. And finally, we examined two applications, public goods provision and market competition, modeled by two-stage network games, and focusing on the time consistency of cooperative solutions. So thank you for your attention.
Thank you very much. Anyone has any questions? Then I have a question. Is it possible to generalize the solution for the end stage game?
Yeah, of course it is possible, and we done it already. But actually, I was thinking this is an educational seminar, so I decided to demonstrate only simple two-stage model. But of course, approach can be adapted for just an end stage game.
Okay, and when you go from the two-stage game to the end stage game, are there any new properties? So can you define or determine any new properties or new ideas related to time consistency? Is it possible or not?
Well, it's I don't know, what do you mean by kind of, what do you understand by properties? So here we focus on time consistency, and when moving from a two-stage game to an n-stage game, so the main problem here is to just to take into account the state dynamics to determine the characteristic function.
Mhm. Okay, and just a short question. Um, when we are taking into account the network structure of the game, the network communication structure of the game, whether it is possible to update the notion of the time consistency, or not update, but is it possible to see a new branches of time consistency related to network, or um, um, to understand some new key points?
Yeah, I got the question. So, well, originally time consistency is connected only to the problem of the revision of the cooperative solution. So when players so what will happen? What will happen if players decide to revise the solution following during the cooperative agreement? So here we just follow the same path. So we focus on the same idea. So what will happen if players revise the cooperative solution? But here we construct the cooperative solution precisely for the network problem. So we use the same concept of time consistency and adapt it for a specific problem, for a particular problem.